So, the way this region is defined, or the way the transition is defined, is through a term called as a subthreshold swing, or in fact the inverse of it, which is the subthreshold slope. Okay. And the subthreshold swing, or the is measured in terms of the volts per decade. Okay. And I will tell you what that means. It means that if you plot the current voltage characteristics on a log scale. So, we plot the log IDS. Okay. So, we say to the base 10, let us say log IDS to the base 10 versus VGS. Okay, I am sorry, VGS, the gate to source voltage. So, till a certain point it is all basically off, and then from here, from say VFB to VT, well, it is not off very far below VFB, just to keep things a little accurate. So, let us say it is off around this region, and from VFB to VT you start having diffusion defining your current, and since the current is proportional to the exponential of the surface potential, okay, which in turn is related to the gate voltage, you will find that the characteristics takes a linear relation on a log ID versus VGS scale, and then beyond VT you start entering the square law dependence of the current. So, this region is our subthreshold region of operation. Now, for us to climb one decade, so it is a log 10 curve, right. So, let us say this is 1e minus 7, and then that is 1e minus 6 and 1e minus 5 and so on, so many amps of current. Okay. So, for us to get from 1 to 1 decade, that is from 1e minus 7, that is to climb one order of magnitude. Okay. So, 1e minus 7 to 1e minus 6, we need to apply a certain amount of gate voltage. So, we have gone from say VGS 1 to VGS 2 for us to get past 1 decade. This voltage difference, okay, divided by this 1 decade is essentially the idea behind your subthreshold swing. How many volts does it take for us to get the current past 1 decade? Okay. So, it is the number of volts per decade. On the other hand, the slope is just the inverse, right. It is the reciprocal of this parameter. Okay. So, it is good to have a better estimate of what the subthreshold swing or the subthreshold slope is. So, the subthreshold swing is defined by dVGS by d log 10 IDS, okay, which we will rewrite as dVGS by d phi s, because VGS is nicely connected to the surface potential, into d phi s by d natural logarithm of IDS, and we will make a correction for the natural log to base 10 log conversion. Okay. So, we have redefined this derivative as with these two terms and this coefficient. Now, how is VGS related to phi s? VGS, so we know this relation. So, all the gate voltage that has been applied is equal to the flat band voltage plus the depletion charge plus phi s, and when phi s hits your 2 phi f, it is called as the threshold voltage. Okay. So, we are now at a phi s below the threshold voltage, that is the subthreshold slope. So, that is the subthreshold region. So, we know that VGS is equal to VGS minus VFP is equal to phi s plus Q depletion by Cox. Now, what we will do is we will define an artifact, okay, or a parameter which is called as a depletion capacitance. Okay. So, I will not call it an artifact, it truly does exist, but the way we will define Q depletion, we will say depletion capacitance effective. Okay. And the way we will define Q depletion is by saying that it is the surface potential into C depletion. Okay. So, what does this mean? So, this means that, okay, you have your insulator, you have your semiconductor and you now have your depletion layer because of all the applied gate voltage, and the electron concentration is very small, they have just started to appear. Okay. So, the way we have defined Q depletion is we say that this is the depletion, this is the band bending, and therefore that is my surface potential, or in other words the surface potential is basically the potential drop across this region. Okay. That is the surface potential, and we say that all the charge here is equal to this potential into this effective capacitance of this region. Okay, so we are treating this as a capacitor. So, we define Q depletion as phi s into C depletion, okay, and make the substitution here. Okay, so you get this relation VGS is equal to VFB plus phi s into 1 plus C depletion by Cox, and therefore the dVGS by d phi s becomes this term, it is 1 plus C depletion by Cox. So, we have solved for this part of our subthreshold swing. Now, in order to get this derivative, let us go back to this relation. Okay. So, here you have your dependence of IDS on phi s, right. So, this is the only dependence on phi s, everything else is independent of phi s, right. So, all this is independent of phi s. So, let us just say that all this is equal to some A times exponent of Q phi s by kT, that is your IDS. Okay. So, my writing it there does not make it appear on the screen. So, we will just say IDS is some constant times e to the power Q phi s by kT, which means, which implies that my natural log of IDS is the natural log of A plus Q phi s by kT, and therefore d natural log of IDS by d phi s is simply, this is a constant, and therefore this is simply Q by kT. Okay, and the inverse of that is kT by Q. So, we can get the second part of this definition, which is d phi s by d ln of IDS is equal to kT by Q. So, therefore, the subthreshold swing is given by this term here. So, it takes this many volts, it takes this many volts to get the current past 1 decade. Okay. So, what does this mean? How do we improve the subthreshold swing? We can improve the subthreshold swing by, we cannot do much with the temperature and we cannot do much with the Boltzmann's coefficient, and you cannot do much with Q, since we will have to change the universe we live in order to do that. Therefore, the only things that are under our control are the depletion charge and the oxide charge. Now, we have, although we have still not defined these things, you will realize that as more parasitic starts developing in the device. So, for example, let us say the interface between the semiconductor and the insulator will have interfacial trap charge. So, all that will add on, because all those regions will trap charge in them and they will all add on to the charge present in the semiconductor. So, any parasitic capacitance that traps charge or contains charge at the semiconductor insulator interface and which lies in the at the semiconductor insulator interface will actually add on to these terms in the numerator, and all such parasitics will effectively start increasing your subthreshold swing and decreasing your subthreshold slope. Okay. So, the subthreshold slope, probably this is a more popular definition, is simply the inverse of the subthreshold swing and therefore, the subthreshold swing will increase, which means you need a larger voltage to head towards 1 decade. Okay. So, that is a lower subthreshold swing and that is a higher subthreshold swing. So, the subthreshold swing will increase as we have more and more parasitics, and the subthreshold slope will decrease as we have more and more parasitics. So, this parameter, the subthreshold swing, is a very key parameter which determines the rate at which the MOSFET goes from the off to the on state. Okay. And you can see that it has got a very fundamental limit. So, let us say C depletion is 0, or let us say there is no parasitic, somehow we have built an architecture wherein all this is minimal and you can almost ignore this term compared to 1. Even then you have a fundamental limit of ln 10 kT by Q being your subthreshold swing. But if let us say C depletion plus C is equal to C ox, okay. So, you could say that this is a basic limit for us to what do you say, there is a limitation of this order in the subthreshold swing. You can't do too much better than this using this present MOSFET configuration. So, therefore, in order to overcome this barrier, we need to re-engineer the MOSFET architecture, okay. And you have many such architectures which try to overcome this barrier, although we will not be talking about them in this course. So, just to summarize the subthreshold characteristics, we saw that your IDS versus let me just use the space a little better. So, let us draw 3 characteristics here. So, we will show IDS versus VGS, and we saw that so let us say this is the VT. So, we saw that there is an exponential dependence on VGS, and then you have an almost square law dependence on VGS after that. Okay. So, you will find that the characteristics of a MOSFET all look like this as you plot the IDS versus VGS. So, this is the transfer characteristics of the MOSFET for different VDS. And as VDS increases, the characteristics gets more and more into the saturation region. So, for very low VDS, you will find that, you remember the subthreshold current also depends on the exponential of the VDS. So, for very low VDS, it is going to be almost, the characteristics would look almost like this, because you are very strongly in linear. Now, you could plot the same characteristics on a log. So, this is the subthreshold region, right. So, technically let us say from VFB to VT. So, you could plot the same characteristics on a log IDS versus VGS scale, and that is quite useful. So, we will have a complete lecture on parameter extraction. So, we will actually look at all these things in good detail there. But what are the useful piece of information that you can get from this curve? From the slope of this curve at very low VDS, or even at any other VDS, if you know the VDS, it is possible to extract this parameter mu C ox W over L, and from that we know what mu is. Okay. If you know the insulator thickness, we can guess what C ox is, but in order to get C ox, we can always do a capacitance voltage curve, okay, and you will find that you know what C ox is. So, if you know C ox and you know the aspect ratio, because we have designed the transistor and we know the geometry of it, you can calculate what mu is from the slope of this curve. But from the log IDS, it is the same data, right. You take the transfer characteristics, the same experimental data sets, and you plot it on a log IDS versus VGS curve. And what you will find is that you will find that the characteristics shows this almost linear relation, and then it bends off, okay, and this region is the subthreshold region, and that region is the linear or saturation region of operation, that is all above threshold. So, in the subthreshold region, you are technically expected to get a straight line because of the purely exponential dependence. But having said that, When we talk about non-crystalline semiconductors, we will see that there are some variations in the subthreshold slope itself because of the existence of states inside the band gap. But for now, for this lecture, what this lecture tells you is that this should be a straight line, because the current is exponentially dependent on the surface potential or then the VGS, and then you have a entry into the above threshold region, and this knee of the curve sort of defines what your threshold voltage is. So, from this curve we can estimate the subthreshold swing, which tells you, which gives you a lot of information on C depletion by C aux, and which you can actually correlate with this CV measurement and iterate with this measurement to make sure that you have the right values, and therefore calculate if there are any interfacial capacitance or etc., etc. Now, this log characteristics also gives you another information. If you look at the current here, which is below VFB, so as to say, okay. If you look at the current here, you will understand what the leakage current in the MOSFET is. So, we have still not approached that boundary, okay. So, we will do that, but a little later. It tells you what is the current between the source and the drain when we think that the MOSFET is completely turned off, which is when we assume that the MOSFET is switched off, that is there is no VGS present. Okay, so, there is VDS, but there is no VGS, and what is the current through the MOSFET, or the VGS is below VFB. So, what is the current through the MOSFET? So, we will talk about the leakage mechanisms in a MOSFET a little later. And the third plot that we looked at was the output characteristics, which is very useful when we design circuits, because it tells us a lot of things about the resistances. So, this is IDS versus VDS, which is the output characteristics of the MOSFET, and that had a form like this, okay. And as you increased VGS, you found that you can get these different family of curves, you can get these different curves, and as we increased VDS, we went from the linear region to the saturation region, okay. And also we looked at channel length modulation, which did not allow these curves to be perfectly flat, but instead gave a dependence on the saturation, provided a dependence of VDS on the for the saturation current. So, this is a summary, a quick summary of our current state of knowledge in the with regards to the MOSFET current voltage characteristics. Now, so we at the beginning of this lecture we said that there are two aspects that we have still not studied. One is the currents below VT, which we have now understood a little better, because these are all the subthreshold currents, and they are all related, they are all governed by the diffusion of electrons from the source to the drain, the diffusion of minority carriers from one of the electrodes to the other. And the second point that we said that we had not covered completely was the variation in the depletion width, which we thought might affect the threshold voltage, okay. And we are going to now address that point. So, what are we doing? We had this very basic model for the current voltage characteristics of the MOSFET, and we are simply improving this model with these details. So, the first model we had was from VT till above to gate voltages above VT, which is all the purely strong inversion characteristics, wherein we looked at the linear and saturation regions of operation, and then we defined the regions, the current below VT, which is the subthreshold currents, and we defined the subthreshold swing, which was an important parameter. And now we are defining the current voltage relation a little more accurately, okay. Although we will just introduce the ideas behind this, but not actually use this for many other purposes, but this is a more accurate model. And this model is something called as a bulk charge theory, okay, and it takes into account the variation in the depletion width. So, as we move from the source to the drain, the initial model, I mean just to restate the introduction, as we move from the source to the drain, not only does the channel charge decrease, but the depletion width is also supposed to vary, and because that is because the p-n junction here is, this p-n junction is more strongly reverse biased as compared to this p-n junction, and this depletion with variation creates an inaccuracy in the way we defined the channel charge. So, in the previous case we had assumed that the VDS is very small, so therefore we got away with many things. We said that the VDS is very small and therefore the depletion width does not change too much, and that is our channel charge, and that Qn is simply equal to your Cox into Vgs minus Vt minus Vc by H, okay, or the charge per unit area is Cox into Vgs minus Vt minus Vc, where the Vt was treated like as though it is a constant, okay. But in reality, as if you take a section here and if you take a section here, since the Vds is different or since the Vc is different, the depletion width is also different, okay. So, it becomes more prominent in this case. So, if I were to take a section here and a section here, the depletion width is suddenly increased, right. So, the depletion width here is XD2, the depletion width here is XD1, and XD2 is clearly greater than XD1. And since the depletion charge depends upon the XD, the threshold voltage in this region has to be greater than the threshold voltage here, and that variation in threshold voltage was completely missed out in our study, because we went from very low VDS and directly into saturation by simply substituting VDS is equal to VGS minus VT, okay. So, that is the little gap in our model, and what we will do now is that we will completely we will try to see how that gap can be corrected for. So, the Vt is got 3 milestone, it is the flat band, you first reach the flat band voltage and then you do Q depletion by Cox, you deplete the region and then you bring the surface potential to equal to 2 phi f. Now, the problem is with Q depletion, right, it is not with phi f is purely dependent on the acceptor ion concentration, VFP is completely dependent on phi ms, and it is only the Q depletion that depends on the value of XD, and it is QNA times XD by Cox. So, as XD varies, Vt must vary. So, near the source side, okay, that is at XD at y equal to 0, this is our XD, that is the depletion width, okay. And near the drain side you have a larger what do you say, depletion width, and that is given by this term. You are all now already very familiar with how to define depletion width in terms of the surface potential, and at any point y, this is the depletion width, it depends upon the potential of the channel there. Therefore, we can correct for our relation of Qn, okay, in this particular manner. So, we will define, so this should we will try to define, this should be Qn into H, okay. It is the the free carrier concentration per unit area, okay. So, particularly I am looking at, or let me just say capital N here, okay. It is the inversion carrier concentration per unit area and not per unit volume, okay, and that is equal to Cox into Vgs minus Vt minus Vc, just like the way we defined, but the Vt is computed at the source, which means using an XD value that is present near the source, which is close to the equilibrium XD value of the p-n junctions, okay. So, we will use that Vt, but then we will correct for it by saying that instead of, you should have we should have actually been using BGS minus Vt of y minus Vc, but we will say that this is equal to Cox into VGS minus Vt at y equal to 0 minus Vc minus Qna into xd of y minus xd of 0, because all the other terms, the phi ms and the 2 phi f terms do not change. It is only this term that we will correct for. Okay. So, essentially we are subtracting Qna xdo and instead adding Qna xdy to this relation here, to this Vt here. And by making this correction, we can now rewrite the differential equation for the drain to source current. We say that IDS is Q n mu electric field into area, where this area is your once again it is the W into H, where the H cancels off, and we say that the current voltage relation or the differential equation that you need to solve is IDS is equal to W into mu into this particular term into dVc by dVy. Okay, and what is this term? This term is nothing but your corrected channel charge per unit area, per unit volume, because the H is cancelled off. So, this is the H and that is cancelled off. So, that is the channel charge. Okay. And you saw now if you see the Vc term appears in your differential equation here as well as here. So, earlier we did not have this term and therefore, we ended up with a square law model, but now with this term being present and you have a Vc to the power half and a Vc term, the model is going to be slightly more complicated than a square law, but it is going to be more accurate because it takes into account the variation in xd. So, this theory is something called as a bulk charge theory, and it generally predicts a lower amount of current. Okay. So, if that was the square law model, the bulk charge theory predicts a current that is slightly lower. And the second point is that the way you define the saturation VDS, that is in the square law model, the VDS saturation, that is the VDS of beyond which the transistor entered saturation, was defined as simply any VDS greater than or equal to VGS minus VT. That definition will change a bit because your current voltage characteristics has now changed. But it is up to you to solve for this exact differential equation as a homework, although in one of the assignments I will put out the exact solution. We will have this as an assignment question, due to which and it is due to that reason that I have not given out the answers here, but we will discuss the exact answer when the solutions to the assignments are presented. So, these are the two key points: the subthreshold slope, the understanding of the subthreshold current, and the bulk charge theory model, which sort of refines the current voltage characteristics that we develop.